Hi, I'm Herb Gross, and welcome to Lecture 9 of Gateways to Mathematics, Gateways to Algebra, where we'll be discussing the concept of a game. In fact, this will be the first of a two-part series called The Game of Mathematics. Now, it may sound kind of frivolous to be talking about the game of mathematics. What do we mean by a game? Do we mean we're going to have the first row compete with the second row and see who gets the answers the quickest? And no, it's much deeper than that. You see, one of the things that's interesting about math is that it's made up almost of equal mixes of things that require great memory and other things that require great logic. And people will say things like, I could memorize everything, but I just couldn't apply the logic. And other people say, well, the logic was okay, but there was just so many other things to memorize. And so the question really is mathematics memory or is it logic? And in a certain sense, the answer is yes. That what we shall see is that if we define a game properly, every single game contains a balance of memory and logic. Now, in trying to define what a game is, I started off with a little riddle over here. Think of all the games that are so different, yet what is it that they have in common? What is it that football and bridge and chess all have in common so that as different as they are, they can all be called games, okay? So the question is this: what looks like a box, smells like cheese, and flies? The frivolous answer, these were great things in the 50s. These were jokes that people told. And the answer, of course, is a flying cheese box. So now you look at this, which doesn't look all that funny, but what happened over here? There were three properties: flying, smelling like cheese, and looking like a box. So we just simply lumped them all together and form one word, one phrase. Now we're going to do the same thing when we talk about a game. What we have to do is, since there are so many different kinds of games, we have to find what is it that all these games have in common so that we can incorporate that. At the same time, we don't want the definition to become so cumbersome that it can't be used. That brings me to the second riddle that this will be based on. And that is, what do you call a little white-haired old woman who rides in an airplane? Answer? A passenger. It doesn't really much matter what you look like, how old you are, what color hair you have. Everybody who's flying on the airplane, other than the crew, is called a passenger. So what we want to do is what? Wind up with a definition that's broad enough to encompass all games, all right, and yet be compact enough so that we can use it. So I guess the theme for this session will be, what is a game? What is a game? Well, think about it. What do all games have in common? Well, they have an objective. And what is the objective? It's to win. Okay, so somebody says to me, I'm going to teach you how to play checkers. I say, well, what's the objective? They say, it's to win. Well, that doesn't tell me much. I say, well, how do you win? It says, you got to capture all of your opponent's pieces. I says, wow, that doesn't look hard to me. So I'm playing checkers. I say to my opponent, hey, look over there. And he turns around, and when he's not looking, I take all the pieces off the board. And now I smile and I say, I've won. I says, you haven't won. I says, yes, I captured all his pieces. He says, no, you're not supposed to do that. I says, why not? Possession is 9 points of the law. Well, possession is 9 points of the law in the game of jurisprudence, not in the game of checkers. You see, if there were a rule in checkers that said, if your opponent is dumb enough to take his eyes off the board and you can capture all his pieces, that's his tough luck, then that would have been a good strategy. You see, the point is, the objective isn't just to win. It's to win in terms of utilizing the rules of the game. So if we look at this, here is my schematic of what I call a game. See, every game has an objective, and the objective is to win. Now, the problem is, how do you win? Well, in order to win, you first have to discuss what the rules of the game are. But in order to talk about the rules, you also have to talk about the terminology, the definitions, the vocabulary. Now, the idea is this. Here's where the memory and the logic come up in any game. Let's see if this doesn't sound right now. Looking at this schematic, only 3 steps, I claim this captures the meaning of every game. A game is any system consisting of definitions, rules, and an objective, where the objective is carried out as an inescapable consequence of the definitions and the rules in terms of strategy. Does that sound okay? A game. Think of any game. See, here's the point. Think of any game you want. This is what I mean by being general. You think of any game you want. We won't say what that game is. When I tell you what my definition is, you decide whether your game agrees with my definition. If it doesn't, then we can't play the game because we have nothing in common, but I think it will. I'm saying this. No matter what game you're thinking of, it's a system that consists of definitions, rules, and an objective where you carry out the objective as an inescapable consequence of the definitions and the rules by means of something called strategy. And this is the diagram that shows us the coexistence of memory and logic. How do you learn the terminology and the rules? You memorize them. How do you apply the strategy? It's logic. And by the way, here's what I mean by memorizing. Let's take a rule of baseball. 3 strikes is an out. Why is 3 strikes an out? Are you going to say because 2 isn't enough and 4 is too many? Why couldn't there be 15 strikes as an out? For example, suppose some kid says, it's very hard for me to hit a baseball. I think 15 strikes should be an out. What do we say to him? We say, look, find a whole bunch of other people who feel the same way as you do, okay? Play a game in which 15 strikes is an out, but please don't call it baseball because that will confuse it with our game that's called baseball in which only 3 strikes is an out, okay? So, by the way, notice if both of these were made rules, we'd be in trouble. How could 3 strikes be an out and 15 strikes also be an out? The first time the batter got 3 strikes, the team in the field would say he's out. The team at bat would say he's still got 12 more strikes. And the umpire couldn't even make a decision because both of these would be rules. You see, the rules are arbitrary, but once you choose the rules, they have to be consistent. Now, the part that's interesting is, if I'm correct, I have now come up with a definition that characterizes every game. But it does more than that. It makes a game out of almost everything that we do. Every subject in the curriculum is a game. For example, the game of good grammar. The game of good grammar, the objective is what? To communicate as effectively as possible, utilizing what? Vocabulary, rules of grammar, etc. Are the rules of grammar self-evident? Or do we just memorize them? For example, here's one that I remember all the time. Never end a sentence with a preposition. Or as the 5th grade joke used to go, a preposition is something you never end a sentence with. See, why is it illogical to end a sentence with a preposition? In fact, the English language, part of which comes from the German, has separable prefixes where sentences have to end with a preposition. Winston Churchill once corrected someone who corrected his grammar by saying, "Young man, correcting my grammar is something up with which I shall not put." I know a sentence that ends with 5 consecutive prepositions. It's about a little boy who's sick in bed. He's up on the 2nd floor. He wants his mother to bring up a book. She says, "Which one?" He tells her. She misinterprets and brings up the one book he didn't want. He looks at his mother and says, "Ma, why did you bring the book from which I did not want to be read to out of up for?" What's wrong with ending a sentence with a preposition? Does that make me a barbarian? No. All the grammar teacher has to say is, look, it's no more logical about ending a sentence with a preposition than it is that 3 strikes is an out in baseball. But in the game of good grammar, this is one of the rules we accept. See? Again, we accept what? The rules and the definitions and try to apply a strategy. And by the way, this also applies to what I call the game of life. Are there rules that we play by in life? Let's take a look. Boy, are there rules. There's society's rules, there's parental rules, there's peer groups' rules, there's your own rules, maybe the rules of the city and the state are contradictory. Here's a game you're playing called the game of life, okay? And these are all the rules you have to play by. It would be like playing baseball with 4 different sets of rules. When you look at all the different rules that you have to balance in your life, and you want a strategy that will allow you to live consistently this way, it's amazing there aren't more people who are living in mental institutions and the like when you consider the pressure that's put on all of us just to get through on a regular day-to-day basis. What I'm trying to lead up to, of course, is the fact that this game idea goes far beyond mathematics But what we're going to be doing as time goes on, both in this lecture and the next lecture, is solidifying what we mean by the game of mathematics. But to show you how important the game is and what we mean by rules and strategy and what have you, let me show you, for example, how we get by as life becomes more and more complicated over here. It's called the game of compromise. See, the worst case is, here's my values, and here are your values, and we have nothing in common. See, with nothing in common, how can we do anything that will be logically compatible with both of us? The rules I accept are not acceptable to you. The rules you accept are not acceptable to me. We might just as well not talk. You see, the best case would be when your values and my values are exactly the same. That means we're going to be playing a game, both of us using exactly the same set of rules. Now, what starts to happen is, when people talk to each other, this fellow over here says, hey, wait a second, your value over here isn't that much different from mine. Would you accept this small change? If the person says no, we forget it. If he says yes, we say fine. He looks at us and says, hey, this seems sort of similar to something I believe in. Would you be willing to make a small change here? Eventually, what happens is we wind up with some overlapping circles. Here are my values. Here are your values. We have some values in common. Here are the values I have, but you don't believe in them. Here are the values you have. I don't believe in those. I allow you to believe these things. You allow me to believe these things. But when we get together, we work only on this portion over here. In other words, what we say is, look, anything that at least one of us doesn't believe in will not enter into negotiations. We will base everything on our common beliefs. And if I can show logically something that comes from our common beliefs, how can either one of us deny it? You see, and mathematics is based on exactly the same thing. One of the reasons I had trouble in math in the 9th grade, or maybe it was the 10th grade, we started to study geometry. And in the geometry course, there were things called axioms. And the teacher said, an axiom is something which is self-evident but can't be proven. Let me just have you take a look at that. What's troublesome about this statement? An axiom is a self-evident truth that can't be proven. Well, first of all, how can it be self-evident if it can't be proven? Evidence seems to have the word evident implies some sort of proof. Secondly, what about the word self-evident? Self-evident to whom? Okay? Self-evident to whom? Suppose I say to the teacher, this rule is not self-evident to me. He says, it better be by Friday because we're having a test on it. You see, it's not self-evident to me. Why is it called an axiom? What should have happened is, the teacher should have said, axioms are rules in the game of mathematics. They may be no more logical to me than they are to you. They may not be any more logical than why 3 strikes is an out in baseball. But the point is, we accept them in order to play the game. But we don't accept them unless everybody agrees. That's why we call them self-evident. We try to pick the rules to be so obvious that everybody will accept them. And our argument will be, if the rules are based on reality, so will our conclusions be based on reality. Take, for example, the axiom, the rule that says the shortest distance between 2 points is a straight line. I don't know how to prove that, but if I said to you, join points A and B by the shortest possible path, do you really think you might say, I think it's this one? Don't you just automatically sort of say, I believe it's this way? And that's all we're saying. If everybody who plays the game believes that the shortest distance between 2 points is a straight line, then certainly anything that's based on that will be acceptable to everybody. Let me show another example. We'll let A and B denote any 2 numbers. Is A plus B equal to B plus A? In other words, if you add 2 numbers, should the answer depend on what order you add them in? Well, let's think about, for example, 3 plus 4. Here's 3, here's 4. If I add these 2 together, would the answer be any different than if I took these 4 and moved them over to here? In other words, in terms of using my fingers, is this many the same as this many? That seems pretty obvious to me. But another person says, wait a second, how come you're using tally marks? I visualize numbers as lengths. See, here's the 3-inch length, here's the 4-inch length, and when I visualize these, I think of a 3-inch length laid next to a 4-inch length, but I could also say what? It starts with a 4-inch length, then there's a 3-inch length, so this is how I view lengths and numbers, and I believe that 3 plus 4 is the same as 4 plus 3. Now, what do we have over here? We have two different people, each visualizing 3 plus 4 in a different way, but all we're saying to them is, keep your individual beliefs. Whatever belief do you have, does your definition of addition and equality allow you to accept the fact that the first number plus the second number is the same value as the second number plus the first number? I call that the Statue of Liberty of education, of compromise. You see, when people first came to this country from other countries with the Statue of Liberty as a symbol, we didn't say to them in terms of the melting pot, come all of you people and learn to think the same way. What the true melting pot spirit was what? Come all you people from different lands who are oppressed, keep your ethnic beliefs, your cultural beliefs, your family beliefs, and we will build a logical law of the land that is compatible with all of your beliefs. We're going to do the same thing in mathematics. It's not as dramatic, but that's what we're going to do. We're going to say to people, what you call equality may not be the same thing as what I call equality. But we're going to focus on the parts that we all have in common and are willing to accept. And the parts that we don't accept, we won't talk about. So let's take a look, for example. See, axioms of equality. That means what? The rules that will govern equality. And I say, okay, for the resulting discussion, A, B, and C are variables, letters, that will stand for numbers. Okay? Now here's what we mean by equality. You think of your definition of equality. Don't tell me what it is. I'm never going to tell you what equality is. I'm just going to tell you the rules that govern it. Any number equals itself. Do you believe that? No matter how you visualize a number, is 3 equal to 3? Is 7 equal to 7? That's called the reflexive property. Any number is equal to itself. I think everybody will agree to that. How about this? By the way, these numbers don't get confused. It's 1, 2, 3, 4, and E stands for equality. See, the second axiom of equality is, if A equals B, then B equals A. In other words, if the first number equals the second number, then the second number is also equal to the first number. That's called the symmetric property. See, it's symmetry. You can flip them. The third one says, if A is equal to B, and if B is equal to C, then A must equal C. In other words, if the first equals the second, and the second equals the third, then there's a bridge that makes the first equal to the third. So in other words, 2 plus 1 is 3. 3 is equal to 3 plus 0. So 2 plus 1 must equal 3 plus 0, if you want to say it that way. But all you're thinking of is called the transitive property. If the first number is equal to the second number, and if the second number is equal to the third number, then the first number is equal to the third number. And when that happens, it guarantees the fourth one that says, if A equals B, then A and B can be used interchangeably in any mathematical relationship. And this is interesting, you see, because we're going to use these rules, but I'm never telling you what equality is. For example, if one person said, I said to him, who wrote Huckleberry Finn? The person says Samuel Clemens. Another person says Mark Twain. Which one is right? They're both right. In other words, these are synonyms. Synonyms mean that they're what? Different names that name the same person. Oh, by the way, be careful. If I say to you, how many syllables are there in Mark Twain? Don't say 5. I said, how'd you get 5? He said, well, Mark Twain's the same as Samuel Clemens. And Samuel Clemens is Samuel Clemens. No. Distinguish between the words and the concept. You see, the words, the names Mark Twain and Samuel Clemens are different. They just happen to do what? Name the same person. 2 plus 1 doesn't look like 7 minus 4. But what do? They name the same number. So wherever 2 plus 1 is the correct answer to a math problem, 7 minus 4 will also be, and we can use them interchangeably. By the way, if you think too lightly of this, you may say, what's so special about this stuff? Well, let me show you another relationship. Remember we talked about Sacramento being the capital of California? So what was another relationship? Is the capital of. Let's see if that's reflexive. Is Sacramento the capital of Sacramento? No, Sacramento isn't the capital of Sacramento. It's the capital of California. Let's check to see if it's symmetric. If Sacramento is the capital of California, does that mean that California is the capital of Sacramento? No. In other words, here's a relationship that's neither reflexive nor symmetric. And transitive doesn't even make sense Because if Sacramento is the capital of California, what is California the capital of that we can even keep the chain going? Let me show you some more of these relationships. How about is the father of? That's a relationship. Is a person the father of himself? No. If the first person is the father of the second, does that mean the second person is the father of the first? No. In other words, if you invert this relationship, it's either what? The son of or the daughter of. Okay? Is this transitive? If the first person is the father of the second person, and the second person is the father of the third person, does that make the first person the father of the third person, or does it make him the grandfather? How about is the brother of? If A is the brother of B, does that mean that B is the brother of A? And before you answer that, be careful, especially if A is named John and B is named Mary. See, John is the brother of Mary. In most families, Mary is not the brother of John. See? Is it transitive, though? If the first person is the brother of the second person, and the second person is the brother of the third person, I guess the first and the third would be brothers. How about taller then? Is a person taller than himself? No. If the first person is taller than the second, does that mean the second is taller than the first? No, it's not symmetric. How about if the first person is taller than the second, and the second is taller than the third, will the first be taller than the third? Yes. See these relationships? Some of them have some of the properties, but not others. How about lives next door to? Do you live next door to yourself? Only if you own both houses. But if you live next door to me, do I live next door to you? Yes. If A lives next door to B, and B lives next door to C, does A live next door to C? Only if the houses are in a circle. See, here's A, here's B, here's C. See, A is next to B, B is next to C, and C is next to A. But if they're in the same straight line, okay, A is next to B, B is next to C, but A isn't next to C. How about is the same height as? Is a person the same height as themselves? Yes. If the first person is the same height as the second, is the second person the same height as the first? Yes. If the first person is the same height as the second person, and the second person is the same height as the third person, are the first and third the same height? Yes. And by the way, when all three of those properties are obeyed, see, if it's reflexive, symmetric, and transitive, that relationship is called an equivalence relation. See, a relation is called an equivalence relation if it is reflexive, symmetric, and transitive. And what that means is this. In an equivalence relation, roughly speaking, if you've seen one member, you've seen them all, relative to what makes them equivalent. For example, let's take the same height as. See, if I see one of these people, have I seen them all as far as height is concerned? If the first person in this group is 6'3", what will the rest of the people be that are in this group? Also 6'3", won't they? But are they equal in other ways? Will they all have the same color hair? Will they all have the same weight? Will they all have the same skin color? Will they all have the same ethnic origins? Will they all have the same skill in mathematics? See, when we say is the same height as, what it means is if you've seen one, you've seen them all, insofar as what? Any question concerning height. So that's what equality is all about. As we go into our next lesson, what we're going to be talking about is whenever we say two numbers are equal, all we mean is what? They have these properties. What else is involved in the game of mathematics? We have to talk about addition, subtraction, multiplication, and division. And what we're going to do is to discuss what rules of the game we're going to be using, and what do you think we're going to do after that? We're going to take those rules of the game and revisit the algebra that we've been studying up until now and show you how these rules of the game enhance our chances to take complicated algebraic problems and reduce them to simpler problems that we hopefully can solve conveniently. At any rate, I think that's enough for this session. Study hard, have fun, stay young. See you next time.